Here's sample test 3, problem number 3. A system consists of 4 particles located as shown. The 4 particles are connected by massless rods. The system rotates clockwise about the origin with a kinetic energy of 5 joules. Find the location of the center of mass of the system. Since we have massless rods, we don't have to worry about the connecting rods. We just have to worry about the location of these masses. And we want to find the center of mass of this, so we want the x, y, and z coordinates of that. If we find the x center of mass, that would be the summation of every mass weighted down by its x position over the total mass of the system. Oops. So that's going to be mass 1, x1, plus mass 2, x2, plus mass 3, x3, plus mass 4, x4, all over mass 1 plus mass 2 plus mass 3 plus mass 4. So if we were to write that out, labeling our masses as 1, 2, 3, 4 as such, then our first mass would be 2 kilograms located at x equal to 0. And then we would have 3 kilograms located at x equal to minus 2, plus 2 kilograms located at x equal to 0, plus 1 kilogram located at x equal to 2. All of our x coordinates over 2 plus 3 plus 2 plus 1. So this is equal to, let's see, 0, 0. We're going to have a negative 6 plus 2 over 8, which would be a negative 4 divided by 8, or a negative 1/2. So somewhere at x equal to a negative 1/2, somewhere along this line, at x equal to negative 1/2, is our center of mass. Okay, what about the y center of mass? It would be the summation of every mass multiplied by its y location over the total mass of the system. And again, that would be mass 1, y1, plus mass 2, y2, plus mass 3, y3, plus mass 4, y4, over the total mass. So if we wrote that out, using our same masses, that would be 2 kilograms at y equal to 1, plus 3 kilograms at y equal to 0, plus 2 kilograms at y equal to negative 1, plus 1 kilogram at y equal to 0, all over the total mass of the system, 2 plus 3 plus 2 plus 1. So this is actually going to be equal to 2 plus negative 2, or 0 over 8, or 0. Which kind of makes sense because we have the 3 and the 1 located on the x-axis, and then the two kilogram masses are symmetrically located about that axis. So our y center of mass is somewhere on the x-axis at y equal to 0. And where those two intersect, that's our center of mass at x equal to negative 1/2, y equal to 0. So we can add to this, since we're in the xy plane, that our z center of mass is actually 0 as well. Okay? What about the moment of inertia? By definition, the moment of inertia is equal to the summation of every mass multiplied by its distance from the axis of rotation squared. And in this case, we are going to be choosing the origin as our axis. So we're not choosing the center of mass, but we're using the origin as our axis. So this is every mass multiplied by its distance from that axis squared. If we were to write this out, that would be 2 kilograms, which is 1 meter away, squared, plus 3 kilograms, which is 2 meters away, squared, plus 2 kilograms, which is 1 meter away squared, plus 1 kilogram, which is 2 meters away squared. So it doesn't really matter positive or negative anyway. We're squaring those distances, so they were going to be positive values no matter what. But it's just our pure distance from the axis. So this is going to be 2 plus 3 times 4, or 12, plus 2 plus 1 times 4, or 4, or 20 kilogram meter squared is our moment of inertia for this system. The rods were massless, so they are contributing no moment of inertia to this system, just the point masses. Find the angular velocity, omega, of the rotation. We're told that the kinetic energy is 5 joules, and the kinetic energy should be equal to 1/2 the moment of inertia times the angular velocity squared. So let's reverse engineer this for the angular velocity. So we have angular velocity is going to be 2 times the kinetic energy divided by the moment of inertia square root. So that's going to be 2 times 5 joules divided by 20 kilogram meter squared square root, which is the square root of 1/2, which is equal to 0.707 radians per second. So that is the angular velocity of the system, 0.707 radians per second, and that is our answer.